Okay, yeah, we need to talk about on a graph of function f, back to talking about it, and there's certain places you can identify on a function from its graph where the derivative does not exist. Here's the first one. Let's think about the function, the absolute value of x. Well, in the absolute value of x, you know, we talked about parts of it anyway. Yeah, on the absolute value of x here, we've got the V shape, right? And so, yeah, let's think about here the derivative. What about the derivative? F prime. Well, from our talks last time, we know that the derivative is equivalent to what on the graph? What is the derivative synonymous with on the graph? It's the slope, right? It's the slope of the line. Now, it's the slope of the tangent line, but you know, here we've just got a line and another line. So, yeah, we're talking the slope. That's what the derivative is equivalent to. You know, and if you have a curved one, you know, you've got to draw your tangent line. But these are just lines. So the derivative is, at this point, say whatever it is equivalent to the slope of that. All right, well, there's no problem with this, with that method of thinking, because, yeah, this line at this point, well, what can you say about the slope at this point right here? The slope is going to be negative, isn't it? Therefore, the derivative is negative. And matter of fact, it's the same slope here, and it's negative. So that's no problem. I've got the derivative is negative on this side of 0. Okay? And we'll talk more specifics at another problem here in just a second. But that's really not the one I'm focusing on now. But what about the other side of 0? Well, to the right of 0, what about the derivative over here? The derivative is positive over here, right? And it's the same positive number, and we'll explain more about that. But right now, what I want to focus on is that corner piece, because we have a slight little problem. We've got a slope coming in negative here, and then the slope's coming in positive here, and then the two meet up at 0. Well, it turns out we have a problem there, like I said. Okay? And we can go back. Let's think about f prime, in this case, of the absolute value of x at x equals 0. And this one we can go back to kind of the definition, splitting up into the piecewise. We know that if it's less than, what do we do if it's less than 0? Well, we do minus x. If it's greater than or equal to 0, it doesn't matter where you put your 0 in this case, because you'll see why in just a second. But anyway, isn't that what we do? Okay. Well, at 0 is the only really point that we have to do this for, where we have to think about it being split. I mean, we have to split it up. If we're at 1, you know, we're in this range. Exclusively, if we're at -1, we're in this. But at 0, there's kind of the two things going on. Coming into 0, I'm negative x. Coming out of towards 0 this way, I'm at just x. So we have to think about that. Well, going back to the limit definition here, what is the limit definition of the derivative? Limit definition says it's the limit as h approaches 0 of f of x plus h minus f of x over h. Here's the thing, though. The thing of it is, as I approach x equals 0, this limit turns into two different things. Here's how. Because if I approach x equals 0, if I approach x equals 0 from, let's see, I don't want to write this. If I approach x equals 0 from the left, if I'm approaching x, then which of these f of x's, which of those f of x's do I take? Well, because there's two possibilities, f of x plus h could either be this or this. But if I'm approaching 0 from the left, in other words, x here is 0, but I'm approaching it from the left, then I get the limit, h approaches 0. If I'm approaching from the left, I have to use this one, the minus x plus h. So that'll be a minus x plus h minus minus x, because like I said, I'm approaching 0 from the left, so I have to use this one, right? Less than 0 side over h. Well, what does that work out to be? That's minus 1 limit as h approaches 0 of minus x minus h plus x over h. The x's cancel. Then I have minus h over h, which is negative 1. However, if I approach x from the right side of 0, then I have to use just x. So this limit becomes the limit as h approaches 0 minus, no, just x plus h, because I'm now using x plus h just is x plus h, and then minus f of x would just be x. Well, the x's still cancel, but what does that leave me with? H over h, which is positive 1. You see the problem there? These limits do not match. So the limit at 0, right, from our previous, so the limit at x equals 0 doesn't exist for this thing right here. What does that mean? Well, if this limit doesn't exist, that's what we're saying doesn't exist, then what else does not exist? The derivative. Okay? So f prime does not exist at x equals 0 for f of x equals the absolute value of x. That's what I'm getting at right here. That's the main reason I went into all this. Okay. Now, does the derivative exist for the absolute value of x here? Yes, because it's a slope. Does the f prime exist here? Yes, it's the slope. However, there's one point it does not exist, and it's right here. And do you see the problem? The problem is it's a corner. It's a corner. This is a corner here, we call it. I don't know if it's a technical term or not, but it's a corner. Wherever you have a corner, which in this case is x equals 0, wherever you have a corner, the derivative for that graph, whatever function it is, does not exist. Because that's what happens, is x equals 0, but the same thing happens for any corner on any graph. If you have a corner on a graph, the derivative does not exist at that corner. Well, it's because, now, so here's what we're saying. So the derivative does not exist at the corner at any corners on a graph. Of a function. Okay? The derivative does not exist at corners, any corners on a graph. Why is it again? It's because the reason it was is because here, as you're coming in, your limit is -1. Coming in here, the limit is +1 for that, the derivative definition of derivative thing. So it's because it's coming in, I don't know, sharply here. Because does the derivative exist here at this point? What about f prime there? We talked about that one last time. It does exist there, and it's because the tangent line comes in at 0. Yeah, slope of 0. Okay, it's because it's a corner. That's why it doesn't exist. It doesn't come in kind of progressively. The tangent lines aren't coming in progressively, I guess is another way you can say it, because the tangent line is -1 slope, tangent line here is +1 slope, and so they don't smoothly come in, because here they're progressing, they're kind of progressing here, here, gradually, and then finally at the top they zero out, level out. Another way to look at it. Okay? But at corners the derivative does not exist. Sharp corners, maybe more specifically. I mean, that one's hopefully fairly obvious. Here, let's just say at 3. Do you see a problem with the derivative there? Yeah, there's going to be a slight problem there for that little derivative too. You run into basically the same sort of problem. Your function is this, and then it jumps to that. So yeah, you're going to have difficulty coming up with the derivative at 3 there. At discontinuities is another the derivative f prime does not exist at discontinuities. That's another place the derivative does not exist. Discontinuities. If you have a jump in the graph, derivative does not exist there either. Again, it gets into the thing, what's your limit here, what's your limit here? Well, the two aren't going to match up very well at all. Okay? And one other, and this one you kind of explain with tangent lines. Take, for example, right here. What's the tangent line at that point that I have marked right there? How would you draw the tangent line in? I mean, you got a tangent line here like this. You got one down here like this. So you got a positive tangent. What about the tangent line right there in the middle? Isn't it vertical? Straight up and down, isn't it? If I drew a tangent line in right at some point in here anyway, it's going to be a vertical line, vertical tangent. Well, what's the problem with the vertical tangent line? What's the slope? Because the derivative is equivalent to the slope. What's the slope of a vertical line? The slope of a vertical line, slope of a horizontal line is 0, but the slope of a vertical line is undefined. Okay? Slope of a vertical line is always undefined. It's kind of the opposite of a horizontal line. A horizontal line, the slope is 0, but a vertical line, the slope is undefined. So what does that mean? The derivative is also undefined. which means it does not exist. So those are the three most common, I guess we could say, places on a graph where the derivative does not exist. It does not exist at discontinuities, corners, sharp corners, and vertical tangent lines, where you have vertical tangent lines. Okay? Everywhere else, you should be able to get a slope of a tangent. So those are the three that we watch out for. So if I had a graph here, let's see, say it, yeah. All right, so it comes in here, makes a little jump, goes up and over, and then, yeah. It goes straight up, and then, oh, I forgot one. Okay, like that, okay. All right, so that's -1, 2, 3, 4, okay. Where do you see, where does f prime not exist? This is f. Well, f prime doesn't exist at discontinuity, so at -1. Doesn't exist at corners. There's a corner. Doesn't have to be, it doesn't have to be the absolute value corner line coming in, then a line coming in the other side. It can be a curve and then corner. Any sharp corner does not exist. Derivative. So x equals 4, and then here I tried to draw it where at some point, yeah, you got a vertical tangent line there. So at x equals 2.